Okay, so hello everyone. Today I will presenting my diabetes prediction project, and my goal is to build a binary classifier to predict whether a person have a pre-diabetes or diabetes. So based on the health indicator data, and the detail of the dataset info is on the slides, and each record contains health-related features like blood pressure, so cholesterol, BMI, age, and lifestyle indicators. And one important effect that I noticed earlier in the dataset is heavily imbalanced, and about 86 percent are non-diabetic, and only about 14 are diabetic. So around 1 to 6 ratio, and for F1 score as a main metric, so accuracy can looks good, and it still fail to detect, but it still fail to detect the minority class. And I started with simplest baseline. So logistic regression was default setting, and when I run the cross validation, accuracy looks high around the mid 18s, and at first glance that feels promising. But the score was much lower than I expected in the cable, so I checked the module actually predicting. So I found it's predicted almost everyone as non-diabetic, and in other words, it achieved high accuracy most by the following the majority class. So I think that's imbalanced data set, and accuracy is misleading, and module can looks good while being predictably useless. So from the point on, I focus on F1, not accuracy. And my next step is to directly address the class imbalance. So I use two simple but effective strategies. So first, I set the class weight balanced in the logistic regression, and it's increased the importance of the diabetes cases during training. And secondly, I optimize the classification threshold, and I did not just use 0.5 instead of I searched a range of the threshold, and selected one that maximized F1 on validation faults. And I saw a clear trade-off. A lower threshold gives a higher recall but lower precision, and a higher threshold improved precision but reduced recall. And after balancing and threshold turn, and I result improving a lot compared to the baseline, and my Kaggle score is increased significantly. And after the module started behave better, and I wanted to understand what features are driving to the predictions. So I ran the feature analysis, use correlation checks, and module signals. And across the different methods, the most consistent and important predictors are gen health, high BP, BMI, diff work, height, and age. So that was assuming because it matched the real world institution. And for example, and so higher BMI and worse the general health are clearly linked to high diabetes risks. So this step helped me in two ways. So one is confirm that the dataset contains two meaningful signals, and it guided me to what to combine and transform in the feature engineering. And based on what I learned, I engineered a few features to capture a combined risk. And because diabetes risk is usually a pattern, so not a single variable. So I added interactions features such as BMI with age, capturing age relative to opposite risk, and high BP with height. So that's capturing a strong cardio risk profile. And I also create opposite composite risk scores by the assuming several keys and binary risk factors like high blood pressure, high jaw and stroke and heart disease and difficult working. And I grouped the BMI into the medical style categories like normal, so overweight and obese. And these engineering features improved my score, but the improvement was incremental, and it helped. But I could tell I was approached performance plateau. And the biggest breakthrough I had was I realized that I should use probability predictions instead of only the hard labels. So at first I just generate a 0 and 1 outputs, but then I switched to use predict probability in the so the module can outputs value uh, between the 0 and 1. So this gives me a confidence score for each person instead of the fixed decision. After I made this change, the improved is dramatic. So my Kaggle score is jumped to the around the mid 7, range about to 0.819, and this was the largest gain in the entire project, so larger than all features engineering gains combined. And for me, this was a key lesson. So sometimes the biggest improvement comes from the using the module output correctly, not from the adding the complexity. And once the probability predictions was working well, and I compared the modules, logistic regression was still a strong baseline. But I also tested the tree-based modules as that can capture the nonlinear patterns better. So I evaluate the modules like the random forest and the gradient boosting. And in my experience, uh, the gradient boosting performed best after turning, and I turned um, key parameters such as number of tree, learning rate, and the maximum dips. So the best figuration was around 200 estimated meters. So the learning rate about the 0.05 and the max dip about the 4. So when the dips increase the feature, the performance stopped improving, and so which suggests overfitting. So with turn module and the probability output, I reached my best performance around 0.820. And to roll up, I improve the performance step by step. So baseline logistic regressions, then the class balancing and the threshold turning, and then the features engineering, then the major breakthrough with the probability predictions, and the final module turning to the gradient boost. So the main takeaway is imbalance must be handled explicitly, and so the otherwise module will ignore the diabetic cases, and the probability outputs create the biggest improvement and in my result, and the feature analysis and the domain logic is the best guide for the feature engineering, and simple well-turned module can win, and especially when the pipeline aligned with evaluation metric. So that's a story of my project in M4. Thank you.